Good day to the CAD lecturers and friends. We are Group 11 and today we'll be presenting our mini project on total hip joint replacement, also known as THR, for NMJ 21003. I'm Samuel Yobunleng with matrix number 241151573. So I'll be discussing about the introduction, project background, as well as the problem statement. Okay, so let's get right into it. All right, for introduction, total hip joint replacement is acknowledged as one of the most successful, cost-effective surgical interventions in contemporary orthopedics, also known as bone surgery. So this intervention becomes clinically necessary when the patient suffers from various diseases that cause the damage to the hip joint. This causes pain and reduction in mobility, which substantially affects daily life. Right, a few common diseases include osteoarthritis, rheumatoid arthritis, avascular necrosis, and femoral neck fractures. So THR becomes the solution when all other non-surgical treatments fail. Now a bit on our project background. So this mini project is driven by the aging global population and longer life expectancy. People live longer and are more active later in life. So this actually increases demand for total hip joint replacement. This pressure actually leads to the significant advances in implant design and materials. However, as of today, our implants only last between 15 and 20 years. Now, when these implants fail, the revision surgeries that are required are not only more expensive, more complicated, they're also more dangerous compared to our initial procedures. So this mini project focuses on three problem statements, which are aseptic loosening via wear, stress shielding, and structural failure at the modular junction. Our mini project attempts to tackle these issues by creating our own model in hopes to extend the lifespan of implants and enhance patient outcomes.
Good day to the senior lecturers and my fellow friends. My name is Ko Kai Yuan. My metric number is 2511522134. And today I will be presenting on the literature review and methodology focusing on AutoCAD 2D. I will begin with the literature review starting with the functional anatomy of the hip joint. The hip joint is a synovial ball and socket joint formed by the femoral head and the acetabulum. Both of these surfaces are naturally covered with the hyaline cartilage, which helps reduce the friction and allows smooth and pain-free movement. According to the literature, during normal walk, the hip joint can experience forces up to 2.5 to 4 times a person's body weight. This high loading condition explains why strong, durable, and well-designed implants are required for the total hip replacement procedures. Early hip replacement designs began with Chanli's low-friction arthroplasty, which used a one-piece stainless steel implant. While this design was successful at the time, it offered limited flexibility for the different patients. Modern hip implants now use modular system, where the stem, femoral head, and liner are separate components. This modularity allows surgeons to customize the implant during surgery to better match the patient's anatomy. However, literature also highlights that modular design introduces a weak point at the head neck taper junction, which may lead to micro motion and long-term implant failure. Material selections plays a very important role in determining the lifespan of the implant. According to literature, titanium alloy is commonly used for femoral stems due to its excellent biocompatibility and lower Young's modulus compared to stainless steel, which helps reduce stress shielding. Ceramic femoral heads are preferred because they produce lower wear rates and are highly scratch resistant. Meanwhile, UHMWPE liners remains the standard bearing surface because they provide low friction and acts as the cushioning interface between components. Despite improvements in design, three major failure mechanisms are still commonly reported. The most common is aseptic loosening, which occurs when polyethylene wear particles trigger bone resorption. Stress shielding happens when a stiff implant carries too much load, leading to bone loose around the implant. Finally, micro motion at the head neck taper junction can cause corrosion and adverse local tissue reaction. These failure mechanisms strongly influence our design consideration in AutoCAD, especially in terms of geometry, dimension, and component fit. AutoCAD was used to generate precise orthographic views of the total hip replacement components. The main objective was to define accurate dimensions and ensure anatomical compatibility before proceeding to any 3D modeling. All drawings were developed based on values obtained from the literature and standard hip joint geometry. For the femoral head, a diameter of 33 millimeters was selected. According to literature, this size provides a good balance between joint stability and reduced wear. The acetabular system consists of polyethylene liner and a metal shell, where the selected dimension ensure sufficient liner thickness to prevent wear through and improve long-term implant durability. The femoral stem was drafted with a total length of 129 millimeters to ensure stable fixation within the femoral canal. A neck shaft angle of 135 degrees was selected based on anatomical standards. This angle helps reduce bending movements at the femoral neck, thereby lowering the risk of fatigue failure and stress concentration. In conclusion, AutoCAD 2D graphing plays a crucial role in implant designs. It ensures dimensional accuracy, prevents assembly errors, and serves as a solid foundation for further modeling and analysis. Without precise 2D drawings, design errors may carry forward into later stages, potentially affecting implant performance and patient safety.
Hi, it's me again. And Autodesk Inventor is my main contribution for this mini project, so I'm going to explain about it. So what is Autodesk Inventor? Autodesk Inventor is a professional grade 3D mechanical design and engineering software. And the tools that we use are extrusion, revolution, sketching, fitting, combination, and many more. All right, the main function of Autodesk Inventor in this mini project is to produce our parts for our design. As you can see here, it is the femoral head, femoral cup, plastic liner, femoral neck, and acetabular cup. All right, once these parts are ready, they are put into Inventor assembly, and with the help of mate and insert constraints, it allows us to create our model. And this model it can be put into Inventor drawing to create an exploded view for a better visual. And so right now you can see here, this is an example of an exploded view for our first model.
Good day to CAD lecturers and fellow friends. I'm Liu Sun Wai from Group 11, matrix number 241151545, and I will be presenting ANSYS part on total hip joint replacement. I will be talking about finite element analysis set up for our mini project. The structural analysis was performed using ANSYS Workbench. Our model is made of 5 components, which are the SW cup, femoral stem, femoral neck, plastic liner, and also femoral head. We assign an alloy named titanium, 6 aluminium, 4 vanadium alloy, also known as titanium 64, to the 3 components, which are the acetabular cup, femoral stem, and also femoral neck. And for the plastic liner, ultra-high molecular weight polyethylene is assigned. Lastly, aluminum ceramic is assigned to the femoral head. Moving on to the contact modeling and meshing approach in ANSYS Mechanical, the simulation setup focuses on the stance phase of the gate cycle, where the hip joint experiences the highest mechanical loads. First, for the head-to-liner conditions, a frictional contact with a coefficient of friction was set to represent the lubricated movement between the femoral head and polyethylene liner. Secondly, the head-to-neck conditions has a bonded contact to represent the firmly locked, more stable connection. Last, for the stem-to-bone condition, bonded contact is also assigned. Following this, a selective meshing approach was adopted for our model. One of the approach is local refinement, which is the default element sizing was applied to the femoral neck and articulating surfaces. This refinement was to capture the high stress, gradients, and contact pressures within our model. Another approach is the global mesh. A coarser mesh density was employed to the distal stem and other non-critical areas. In the end, the final discretized model consisted of 8,925 nodes and 3,940 elements. Furthermore, boundary conditions were applied to simulate the single leg phase of walking. One of the boundary conditions is fixed support. We assign a fixed support at the stem and cortical bone with 0 degrees of freedom. The other boundary condition is the physiological load. We assign 3 different loads, which are the 300 Newton, 1000 Newton, and 2500 Newton to the superior surface of the acetabular cup. Lastly, 4 parameters are assigned, which are the equilibrium stress, total deformation, equivalent elastic strain, and safety factor. So this is the tabulated results of all three main parameters, which are the equivalent stress, total deformation, and also the equivalent elastic strain.
Hi, I am Yong Wei Ming. My ID is 2511-52190. I will talk about result and discussion. Since my teammate cover the simulation setup, mesh generation, and material properties, I will focusing on the load case application first. For the vertical force, we pushed it down on the cap with 300 Newton for the baseline test, and then we move to 2,500 Newton to stimulate the peak weight during walking. Second, torsion. We twist the head with 50 Newton meter to stimulate the friction of the hip turning. Finally, we apply a fixed support to the bottom of the stem, stimulate how the implant hold the tight bone. Two important things to note here. The stress is very low and the stability is high. First as all, even at the maximum load of 2,500 Newton, the stress is only 44.58 megapascal. We are using less than 5% of the material strength. The stability is high because the maximum movement recorded was 0.01 millimeter. For your information, a sheet of paper is about 0.1 millimeter thick. Our implant moves 10 times less than the thickness of a sheet of paper. This proves that our implant is incredibly stable and predictable. Looking at the table, you can see a clear pattern. When we increase the force from 300 Newton up to 2,500 Newton, the stress and the deformation rise in a perfect straight line. To officially validate our design, we need to calculate the safety factor by using engineering equation yield strength material divide the maximum equivalent stress. The stress tells us if the metal about to crack. The maximum stress we found only 44.5 megapascal. The titanium we use can handle up to 818 megapascal before it's deformed. This means that our stress is tiny compared to what the material can actually take. Finally, we calculate the safety factor. In biomedical engineering, usually it must be greater than 2. It means that the implant can hold twice stronger as it need. Our design achieve a safety factor of 19.7, is almost 10 times higher than the requirement. We also look at the deformation. We want to see it if would bend too much. If move only 0.01 millimeter, that is thinner than a human hair, this proves that the stem is extremely rigid and stable. Our discussion is focused on a 70 years old man who was 60 kilogram and its body weight is 589 Newton. We test our design as which is 4.25 times higher than the patient body weight. This proves that our implant can handle load far higher than what the patient will experience in their daily life.
Moving on to the first modification, our group proposed a complete geometric sheet design, contrast to the original model. This design consists of three orthogonal metal polyethylene cuboid articulations. As you can see in the figure, there are three different metal cuboids, the flexor, rotator, and abductor. Theoretically, this design proposed a lower wear than the original bolt and socket design in the original model. Okay, so this is the 3D drawing of our first modification design. So this is the tabulated results of our first modification design. Based on our findings at finite element analysis, I want to highlight that the difference of neck strain increased by 251%, as you can see in our table. This indicates the first modification design experienced uneven distribution of stress at the joint, although the friction of torque was neutralized. It converted the rotational energy into a severe bending moment. In addition to that, these are the images of all three parameters. Since the first modification was not successful, our group proposed a second modification. In contrast, second modification thickened the femoral neck's cross-sectional area The cross-section is increased from a 9.5mm times 7mm slot shown in our figure 1 to a 10mm times 12mm slot in figure 2. So this is our tabulated results for the modification 2. I want to highlight that the equivalent stress was reduced by 11.87% and total deformation is reduced by 9.51% by thickening the neck. This confirms that increasing the section modulus is an effective strategy for managing gait cycle loads, which are the loads mimicking the real-life hip joint. Hence, our modification 2 is a successful optimized design. Following this, these are the results for our modification 2.
In our material selection analysis, we compared 316 stainless steel with titanium alloy to see how the material affects the mechanical longevity of the hip replacement. Okay, based on our ANSYS results, it's found that the total deformation of titanium alloy is more than 50% compared to stainless steel. And initially, this sounds like an engineering disadvantage, but in terms of biomechanics, it's actually a strategic benefit. Titanium alloy has a Young modulus of 110 gigapascals, which is around half that of steel, and in such allows it to have significant greater elasticity during the standard gauge cycle. And right now I'm just showing our FIA analysis for stainless steel. All right, back to why titanium alloy is more superior to stainless steel. Well, apart from its high flexibility, it actually has the ability for osteointegration, which is very good for bone healing. And on top of that, titanium alloy is actually lighter than steel. The density of a titanium alloy is only half that of steel. And as such, our final design combines titanium alloy with the model in modification 2 to produce a more stable THR.
Myself, Devini Armugam. My metric number is 2411545052. So here is the conclusion part. So the project also demonstrates how modern CAD tools allow patient-specific implant design using imaging data, improving fit, stability, and load transfer. Although CAD and simulations provide valuable insights, challenges such as wear stretch shield and varying loading conditions remain overall. Overall, this study emphasized the importance of integrating biomechanicals, material science, and engineering design to improve the long-term performances of total hip replacement. Outcome of the project is the proper design of the total hip replacement using AutoCAD Inventor and ANSYS simulation process. The design of the joint replacement done accordingly to the normal dimension of the orthopedic to ensure that the transfer of the load is done correctly. The stress analysis indicate that the design is capable of handling the pressure equal to the weight of the body. The project proves the importance of using computer-aided design and simulation software as to design the joint replacement, failure reductions, and consequent improvement performance of biotribology in the joint replacement. At the end of summary, the design of total hip replacement is effective. The recommendation, the primary focus on the analyzing how design, geometric and material selections influence stress distribution and deformation in the total hip replacement system. By narrowing the scope and study aim to generate meaningful engineering insight. Within the construct of the student level project, the project focuses on the femur, stem, and acubular components, where different design variations and biomaterial are evaluated. CAD models of these models were imported into ANSYS for infinite element analysis. Standard biocompatible materials such as T64I/4V and cobalt chromium MO alloys were considered to their widespread clinical use and known mechanical properties. Static structure analysis was performed by applying physical loading conditions that represent daily activities, while appropriate boundary conditions were defined to stimulate fixation within the femur. Key performances metrics include one maze, stress, total deformations, and strain distributions. Special attention was given to the stretch shield effects and caused by stiffness mismatch between implant and bone, as well as wear considerations at the femur head as a acebular liner interface. Although fatigue and long term were not fully stimulated, their importance is implanted longevity is acknowledged and discussed based on established orthopedic principle. That's all from our group. Thank you very much.